Okay, so what we want to look at now is orthogonality of vectors in a vector space, right? And in order to determine if vectors in a vector space are orthogonal, right, we're going to use an inner product to check to see if they're orthogonal, right? Right, so before I get into the formal definition of what an inner product is, right, I will recall an example of something that is an example of an inner product and an example of an inner product that you should know already, and that example is called dot product. Right, so if I have two vectors in the plane, right, which means that each vector is just going to have two components in it. And okay, so in this textbook here, the one vector in the plane is v, one vector in the plane is w. Your components for the v are v1 and v2. Components for the w are w1 and w2, right? And the dot product of the vectors v and w you get by multiplying corresponding components, right? So v1 w1 and v2 w2, right? And then what you do is you add those products, right? Okay, so for example, here if I want to get dot product of the vector 2 minus 3 with vector 4, 1, right? You multiply the 2 with the 4, you multiply the minus 3 with the 1, and then you add those products, right? So 2 times 4 would give you 8, minus 3 times 1 will give you minus 3, so you're going to get 8 minus 3, which is 5, right? Right, so our next example, now here what I have is the vectors here written as column vectors, right? But in this section, most of the time, if not all the time, we're gonna write the our vectors in row vector form over here, right? Okay, and it's the same definition of dot product, right? So, except well, you just need to be a little careful about your notation, right? Okay, so I want to take the dot product of this vector 2, 3 with the vector minus 3, 2, right? And how do you do that? Well, it's 2 times the minus 3 plus 3 times 2, right? And this would give me minus 6 plus 6, which is equal to 0, right? Okay, so these vectors over here, and is drawn over here, that the vector u, this is the vector 2, 3 over here, and this is the vector minus 3, 2, right? And what you want to notice is the dot product is, in this case, 0, right? And what that means is that the vectors u and v are orthogonal, right? They in the plane they're at 90 degrees to each other, right? Okay, so if you have a dot product of being equal to 0, it means that uh, it means at least if you're looking at vectors in the plane, right? Then a dot product equal to 0 means that the vectors that you have are at 90 degrees to each other, right? And what a dot product is doing for you is a dot product is giving you an idea of the angle between vectors, right? So dot product v with w, right, is measuring the angle between v and w, right? Okay, and how you do it is you'd use this identity here, right, which I'm pretty sure you've seen already, right? So if you want to get an idea of the angle between vectors v and w, right, what you do is you work out the dot product here, and you need to divide by the magnitude of the vectors, right? And that's going to be equal to cosine theta, right? And then from that you can figure out what theta is, the angle is between the vectors, right? Okay, so in the case when such as over here, right, when a dot product works out to be 0, right, then what you're going to have is you're going to have cos theta is equal to 0, and that's going to tell you that theta is going to be equal to 90 degrees, right? Assuming that you're measuring it in the correct way, right? Okay, and we can take dot products of any vectors, right? Once the vectors have the same length, right, and they don't need to be just vectors with two components or vectors from the plane, right? Or vectors with three components. It could be any length over here, right? The only thing is when you're taking a dot product over here, both vectors need to have the same length, right? Okay, so as an example over here, what I have is you have vectors with 4 components, right? So this is an element of R4. And you have a vector also belonging to R4. And you can take a dot product here, right? And you take a dot product in the way that, same way that how it was defined for vectors in the plane, you're just going to multiply corresponding components, right? Okay, so here it's 2 times minus 1, right? You see the 2 times minus 1, 0 times 3, minus 3 times 1, and then 1 plus 2, and then you add all of those up, right? And you'll get this number, which is minus 3, right? So when you work out a dot product, you're going to get some scalar over here, right? Okay, so this is for vectors in R4, right? And we can also do it for vectors in R3, of course, right? So okay, so for example, here I have a vector 1, 1, 1, right, in R3. Notice this is in row vector form. And I have a vector 1, 0, minus 1, right? And when I take the dot product of these, right, it's not hard to see what I'll get is 1 plus 0 plus minus 1, which is going to be equal to 0, right? So the dot product is actually going to be equal to 0, right? Okay, so your vectors are shown over here, right? The black one here is P, right? And the blue one here is Q, right? And these are in fact at right angles to each other, right? In three-dimensional space, right? It's right. You're not seeing exactly the right angles because you'll see the right angles. Uh, P and Q are going to form a plane for you in three-dimensional space, right? So if you just project onto that plane, right, then you would see the actual 90 degrees over here, right? So that's why I'm rotating it around to show you the 90 degrees, right? But if you look at it in normal perspective here, say it this way with X and Y, right? You're not quite seeing the fact that it is at 90 degrees, right? Okay. Alright, so I can take a dot product of vectors in three-dimensional space, in four-dimensional space, in two-dimensional space, any dimension that I need, right? The main thing is that the vectors, when you're taking a dot product, they need to have the same length. Right, so let's consider the definition of an inner product now, right? So I have a vector space, right? And what I'm going to do now is, for this vector space, if I have any two vectors, I can combine them, right? So any two vectors, such as vectors u and v, I can combine them and combine them in such a way that I actually gonna get a number over here, right? Okay, so that is what this sort of odd notation over here means, right? You're gonna be looking at functions from pairs of vectors, right? And a pair of vector would have a u in it and a v in it, right? And those the vector u and v, right? So a vector such as the u and v over here, what you're going to do is you're going to combine it somehow to get a scalar, right? So what you have is a map from pairs of vectors into reals, right? So how you want to read this is if I have two vectors, you're going to combine them somehow to get a scalar, right? And that is a function, right, on pairs of vectors like this, right? Okay, so let me give you an example of such a function between from pairs of vectors, right, to reals, right? So in other words, if I'm gonna have any two vectors over here, I'm gonna combine them somehow so that I get reals, right? Okay, so my vector space over here is R2, right? So this big V over here is the plane, right? And so I have two vectors in the plane and I want to combine them somehow to get a scalar, right? So u is a vector in R2 and v is a vector in R2 for this example. Okay, and the vector u I can write out, right? U is vector with two components and v is a vector with two components, right? And how I'm going to combine them in this case is I'm going to take a1 and multiply it by b1 and a2 multiplied by b2, right? And then add them, right? And you want to notice, well, what I'm doing over there is I'm just taking the dot product of the vectors u and v, right? Okay, so what this function is doing for me is that if I have a vector u inside and a vector v inside there, right? How I'm going to get the scalar is from the vector u and v, I'm just going to take the dot product of them, right? And that's going to give me a scalar, right? Okay, so this is an example of how you're going to define a function that is an inner product, right? Okay, I need to still justify that it satisfies these definitions over here, right? But to start with, I want you to see how this sort of function definition works, right? You want to think of it as you're taking a u from here, you're taking a v from here, and you're combining them somehow to get a scalar, right? Okay, and in this case, how you're going to combine them is you're just going to take the dot product of the u and the v, right? Okay, and this is normal dot product that I just talked about for vectors in the plane, right? So if you want an example, if I have a vector u which is 1, 1 and a vector v which is 1 minus 1, so both of these belong to R2, right? Then the inner product of the u and v, right? What you're going to do is you're going to combine these somehow to get a scalar, right? And in this case, well, you're just using dot product, right? So it's going to be 1 times 1 and then 1 times minus 1, right? Okay, so your inner product of the u and v turns out to be equal to 0, right? Okay, so this inner product over here happens to be just normal dot product over here, right? But what we're going to see in this class, right, is that your inner products do not always need to be just dot products here, right? Okay, so in this particular case, your inner product over here is a dot product, right? One thing we want to note is, and this might be useful for us, is that if I'm taking, we could forget about the inner products for the time being. If I'm taking a dot product of the u and v, right, I can actually achieve that by matrix multiplication, right? Okay, so if I have vector u, which is the 1, 1, and vector v, which is the 1 minus 1, right? Let's notice that if I consider this matrix product over here, where I have the vector u in row vector form, and what I do is I take the transpose of this row vector v, right? When I take the transpose of the row vector v, I get 1 minus 1, right, in column vector form. I notice I can do my matrix multiplication over here, right? This is a 1 by 2 vector here by a 2 by 1 vector, right? So when I do my matrix multiplication over here, right, I'll get 1 times 1, which is this, and then 1 times minus 1, right? And I get a 0, right? Okay, so strictly speaking, if I'm multiplying these as matrices, I'd have a 1 by 2 by a 2 by 1, so I'd have a 1 by 1 matrix. So really, I'd probably want a bracket around this to indicate that it's a 1 by 1 matrix, right? But for us in this class, what we're going to do is we just think of 1 by 1 matrices as just scalars, right? Okay, so your vector, your dot product u with v, you could actually work out as u times v transpose, right? And this comes in handy, right, to prove certain things, right? Okay, right, so just looking at dot products, right, dot products satisfy these properties here, right? Okay, so you probably saw this one already, that if you take a dot product of u with v, right, and you work it out, it's the same as if you you put v in front and you put the u afterwards, right? You'll get the same answer, right? Okay, so this is an example of a symmetry property for a dot product, right? Okay, it doesn't make a difference which order you do this in, you're gonna get the same answer, right? Okay, now we have this property over here, which is linearity in the first argument, right? So, well, what's your first argument, right? The first argument is your first vector over here, right? And what you want to notice is that in this case, how I have it written over here is that this first vector is in fact a sum, right? And it's a linear combination of two vectors u and v, right? Okay, so I have a linear combination in my for my first vector over here. So first vector is, you want to read that as first argument, and you're going to take the dot product with w, right? And the idea is that this plus will distribute over the dot product over here, right? So what you could do is you could take dot product of u with w, right, and then multiply it by a scalar over here. Take dot product of v with w multiplied by a scalar b, and then finally just add it up, right? Okay, so this is just normal. You can think of this as, say, like if you just had normal, if you had addition of real numbers and you're multiplying by a real number over here, the addition will distribute over the multiplication, right? So that's sort of really what's going on over here, but yeah, we don't call it distribution over here. In context of inner products, you call this sort of property linearity in your first argument, right? Okay, and this one here is if you take a dot product of a vector with itself, right? Then what you're going to get is you're going to get something that is bigger than or equal to 0, right? So, okay, so let's take a look at this, an example of taking a dot product of a vector with itself, right? So I have these vectors in the plane, and what I'm going to do is I'm going to move this v over here using this software so that the v lines up with the u, right? Okay, so in this for this situation over here, notice the vector v is the same as the vector u, right? Okay, now when I take the dot product of the vector, two vectors which are identical, right? So notice this 2, 3 over here. So this is a u over here, and this is u also, right? So taking a dot product of a vector with itself, right, like this, right? Well, what's happening over here, right? Notice what you're doing is you're squaring your components, right? So it's 2 times 2, which is 2 squared, and then 3 times 3, which is 3 squared over here, right? Okay, so this over here, even if you had a negative inside there, right? And I'll do an example in a second, right? But the main thing is this is 2 squared plus 3 squared over here, right? And what you would get is you would get a positive answer, right? Provided that your vector was in the 0 vector to start off with, right? So let's see a next example of taking a dot product of a vector with itself. But now what I want is one of the components to be negative, right? To illustrate the fact that I'm going to be squaring the components, right? So what I have is two vectors over here that are the same. I have minus 3, 2, and I have minus 3, 2, right? Okay, and I'm taking the dot product over here, right? Now when you take a dot product over here, you're going to have minus 3 times minus 3, right? And the minus 3 times minus 3 is minus 3 squared, right? And that's positive, right? And then I have 2 squared over here, and that's also positive. So I'm adding two positive numbers over here. So this is going to be bigger than or equal to 0, right? So that's the idea over here, right? If we take a dot product of a vector itself, it's going to be bigger than or equal to 0. And the only way that it's going to be equal to 0 is if each of your components over here were equal to 0, right? So that is what this property of the inner product is saying, right? And this is called your positive definite property for inner product, right? Seeing that, well, I have this nice software over here. I'll give you an example of u dot product of u and v is equal to dot product of v with u, right? So it doesn't make a difference what order you have this in, right? Okay, so for example, here I have dot product of u with v, right? Where u is minus 1, 4, and v is 4, 0, right? And here what I have is the vectors reverse, right? Here I have 4, 0, and minus 1, 4, right? Okay, so when I work out this dot product over here, it's going to be minus 1 times 4, right? When I'm working out for that component, I'm going to have 4 times minus 1, right? But the idea is that minus 1 times 4 is the same as 4 times minus 1, right? And likewise, when I have this 4 times 0 over here, the 4 times 0 is the same as 0 times 4, right? So when you're looking over here, here I have 4 minus 1, and here 4 times minus 1, and here I have minus 1 times 4. So it's the same thing. Here I have 4 times 0, and here I have 0 times 4, right? And because these inside over here with the products is just multiplication of real numbers, could always change the order, right? Okay, so that's basically why it doesn't make a difference when you take in dot product, what order you have the vectors in. Okay, so let me show this property of your dot product, which is linearity in the first argument here, right? Okay, so how I'm going to do that is, remember I said that if the dot product of u and v I can write as a matrix product u times v transpose. So that's what I want to use here to show this, right? Okay, so I have this expression on my left hand side, right? What I'm doing is I'm taking a dot product of au plus bv, taking a dot product of that vector with w, right? And that's the same as taking the vector au plus bv and multiplying it by w transpose, where this multiplication over here is matrix multiplication, right? Similar to what I have over here, right? Okay, but once I have, so this over here is a vector, or you could just think of it as a matrix, right? So I have a matrix here and I have a matrix here, right? And then I have a sum of matrices being multiplied by a next matrix, right? And the matrix multiplication can always distribute over sums, right? And we saw that already, right? So for example, if I have a matrix A over here, and I have a sum of matrices x and y, right? Then I can distribute the multiplication over the sum, right? So I get ax plus ay, right? So what I'm doing here is I'm using a property of matrix multiplication, right? I'm not saying that doesn't require some proof, but we're gonna just take that as fact over here, right? So this is matrix multiplication. You have a sum over here being multiplied by a matrix, so your matrix multiplication would distribute over this plus, right? Okay, and when it distributes over the plus, this is what you're going to get. You're going to get AU times this matrix here, BV times this matrix over here. But then this U times W transpose is U dot W, right? And then V times W transpose is V dot W, right? Okay, so notice what you have. You have what you want, right? That if you have a sum over here and you take the dot product with W, this sum will distribute over the dot product, right? So you're going to get AU dotted with the W, and then you're going to get the dot product BV with W, and then you're going to add those, right? Okay, so that shows you linearity in the first argument by using the fact that a dot product you can regard as matrix multiplication. Alright, so remember what I said, right? If I have a vector space, okay, what an inner product is going to be is an inner product is going to be a function, right, that will take pairs of vectors, so vectors u and v, and it will return a scalar over here, right? Okay, and for such a function to be an inner product, right, it needs to satisfy these three conditions here, right? And these three conditions are what I just talked about. But I talked about them for just a special case of dot products, right? But this is a more general criteria if you want, right? So for a function, right, on pairs of vectors, right, a real valued function on pairs of vectors, in order for it to be in a product, it would need to satisfy these these three conditions over here, right? And if you want to understand this, and you're just looking at this definition here, right, to understand it, right, really the easiest way to understand this is you could just really think of this this sort of inner product as just being normal dot product, right? And if you just think of this as just being normal dot product, right, and I in fact do it over here, right, if you just think of this as being normal dot product, then you're starting to see that the properties make sense geometrically, right? So for example, if you take an inner product, if you take a dot product with a vector, with an x vector, it doesn't make a difference what order you do it in, right? Okay, and then here the inner product would distribute over the sum over here. And here what this is saying is that if you take an inner product of a vector with itself, right, if what you have is in fact the inner product, then it must have the property that when you take an inner product of the vector with itself, you're supposed to get something that's going to be bigger than or equal to 0. And the only way that you're going to get something that it is actually equal to 0 is if the vectors themselves are equal to 0, right? Okay, so a function on pairs of vectors is an inner product on a vector space if this function on the pairs satisfies these three conditions, right? Okay, so let's look at an example of something that actually is an inner product, right? And we'll do it, say, for this general case of Rn, right? Now, if you're not happy with this Rn, you could think of the small n as being, say, like R2, R3, or R4, and so on, right? Okay, so these are vectors, right? Rn is vectors of length n over here, right? And what we're going to do is we want to define a function, say vector space over here is Rn, right? So you want to define a function on pairs of vectors, right? Okay, and how you're going to define your function on the pairs of vectors is you're just going to take a dot product, right? So I'm defining this function over here to actually just be inner product, right? Okay, and if this function over here actually is just inner product, right, then it satisfies these three conditions, right? And so it will be inner product, right? Okay, so some function defined on pairs of vectors, in order to show that it is an inner product, it needs to satisfy these three conditions, right? But what I'm talking about here, what I'm defining this function to be, is I'm defining it to be dot product, right? Okay, so what that means is that the fact that this function over here on pairs of vectors is dot product, and we saw that dot product satisfies linearity in first argument, satisfies symmetry, and satisfies positive definite, right? We expect that this function, so defined as a dot product, is going to be an inner product, right? Okay, so if I have Rn and I define a function on the pairs of vectors as just taking the dot product of the vectors, then that's an example of an inner product, right? And that inner product has a name. It's called dot product, right? Or it's called standard inner product, right? So by standard inner product, it means it's sort of like your most basic case, and the most basic case, if you want, of an inner product on Rn is dot product, right? Okay, now what I do over here in the notes is I prove it. Okay, I went through an argument here to show that the dot products satisfy your three required conditions, right? But I also do it here, right? More formally, right? Okay, so let's go through it, right? Since it's already here, right? So what I do is I have the sum linear combination of the vectors u and v, right? And I'm going to be taking the inner product with w, right? So here I'm just writing out everything, writing out what the u is, write out what the v is. The v is v1 to vn, and I write out what the w is, w1 to wn, right? So I just write out what the components are, right? Okay, and here on this side here, what I do is I add the vectors, right? So I multiply the a by the vector u, multiply b by the vector v, right? And then I actually add the vectors, right? I still didn't take the dot product as yet, right? And now going from this line to this line, what I do is I actually do take the dot product. So it's this first component over here times w1, right? And last component over here times wn, right? And these dots over here are supposed to indicate that I'm going to do the same thing for corresponding components in between, right? Okay, so now I get this over here, this sum, right? And these are just scalars, right? And what I could do is I can expand this out and just collect, right? When I expand it out and collect, you can show that this line over here is equal to this line, right? And you could really just check the individual terms, right? So here what I have is w1 times a u1, right? And notice this is w1 times a u1 over here, right? And then I have w1 times bv1, right? Which is this w1 times bv1, right? Okay, and here I have a times un wn, right? And here I have a un times wn, right? And here I have b times vn wn, and here I have b wn times vn, right? So the terms over here correspond to the terms over here, right? So I have an equality over here, right? And what you want to notice is that this inside over here, this is dot product of vector u with w, and this inside over here is dot product of v with w, right? And here I pull the a and the b outside, right? So you pull the a and the b outside over here, right? And this gives you a required statement for linearity in the first argument, right? Okay, so symmetry is easier to see, right? I'm taking dot product of u and v, right? That's what this inner product is defined to be. So first I just write out what the components of the vectors. Take the dot products, u1 with v1, un with vn, and so, right? And the point is that these are scalars, right? So because these are real numbers, I could just exchange the order of the multiplication with these, right? That's what I do over here. And this, as defined, is a dot product of v with u, right? Inner product with v and with u, right? Okay, and to show the positive definite property, right? Taking a dot product of a u with itself, right? So again, I just write out what the components are. U is a definition of dot product, which means is u1 times u1, which would give me u1 squared, right? For the last component over here is un times un, which is un squared, right? What I have is each of these, remember I'm working over a vector space in the reals, right? So each of these are just real numbers over here, right? And once u1 squared, right? Once you square a real number, it's going to be bigger than or equal to 0. So each of these are non-negative. So if I add up non-negative numbers, I get something that is non-negative, right? Okay, so that shows this part over here for the positive definite, right? But then there's also this part over here, right? The only way that inner product of a vector with itself is going to be 0 is if the vector is equal to 0, right? Okay, and how you'd show that is you could just really consider this equality over here, right? So you're taking the inner product with the vector with itself, right? This, and you set it equal to 0, and you want to see what's happening, right? Okay, so if I have this over here, the inner product of a vector with itself is equal to 0, right? I just work out what the dot product is with u with itself, and I did it up here. That's just the component squared, right? So have the component squared being equal to 0. And again, these are just real numbers over here, right? I'm just working over reals. And the fact that each of these are bigger than or equal to 0 and they sum to 0 means that each of these must be 0. Okay, so each of your components, u1 to un, must be 0, which means that the vector is equal to 0, right? Okay, so that in fact shows one direction. This is if and only if, right? Okay, so what I just showed is if I have the dot product of the vector with itself, if the inner product of the vector with itself is equal to 0, then the vector must be equal to 0, right? Okay, but I can always just go in the next direction, right? And really I just reverse this argument over here, right? So if I have a 0 vector, right, it means that all the components are 0, right? And if all the components are 0, if I square all the 0 components, I'm just going to get 0. And the square of the components, sum of the squares of the components, is really just taking the dot product of the vector itself, right? So if you take a dot product of 0 with 0, you're going to get 0, right? So what this is saying is if the vector is equal to 0, right, then when I take the dot product of 0 with itself, I'm supposed to get 0, right? Okay, so that's your two directions, right? So this would be how you'd show it formally, right? And I'd expect you to know this, right? How to do this. Okay, so let's consider again a function on pairs of vectors, right? But and vectors on from R2 in this example here, right? All right, so how the function that I'm gonna look at over here is not going to be dot product. It's going to be different from a dot product, just actually a small variation in a dot product, but not the same thing, right? Okay, so how I'm gonna combine these two vectors here, u and v, to give me a scalar, right? Is I'm gonna use this expression here, right? Okay, so I have vector u, right, times a 2 by 2 matrix, right? And the 2 by 2 matrix is this 2 by 2 diagonal matrix here, right? So the big D stands for diagonal matrix, right? Okay, and then so u over here, which is my row vector, this 2 by 2 diagonal matrix, and then this column vector, 2 by 1 column vector, right? And notice the matrix multiplication is well defined here, right? Because this is 1 by 2, right? This is 2 by 2, and then this is 2 by 1, right? So your matrix multiplication is defined over here, and once you multiply these out, right, what you get, once you multiply these three matrices together, you're going to get 2u1 times v1 plus u2 v2, right? So I get this function over here, right? So this is a way of given any two vectors in R2, I can associate a scalar to them, right? So that is, it's a function on pairs of vectors to reals, right? Okay, and I wrote over here, what I did is I wrote down just what the normal dot product is, right? And what the normal dot product is, well, it's u1 times v1 plus u2 times v2, which is this over here, right? Okay, so this is when you combine the vectors u and v using just normal dot product. And this over here is when I combine using this sort of, if you want, modified dot product, right? I shouldn't call it that, right? Okay, so this here, notice that this function here is not the same as this function over here, right? You're not going to get the same values over here as over here, right? So what this is this here, we're going to show that it's an inner product, so that we're going to show in a second that this sort of function on pairs of vectors will satisfy these three properties, right? So this is an example of an inner product, right? But this inner product is not the dot product, right? So we just saw the dot product is an example of an inner product. What we have over here is a next example of an inner product, and these are different examples, right? Because this function here is not the same as this function over here, right? So the point I want to make over here is that your inner products on R2, right? It's there's more than just the dot product, right? You also have other inner products that are not equal to the dot products, right? But the nice thing is for Rn, right, you could actually classify the types of inner products that you're going to have, right? The types of inner products that you're going to have would always take this sort of form, right? U times A times V transpose, right? Notice it's the same form as this, right? Here, what I'm using is the big D is a diagonal matrix, right? This matrix A over here doesn't need to be a diagonal matrix, but it needs to have certain special properties, right? So that the overall function is going to be an inner product, right? And certain properties that this matrix A needs to have is actually that it needs to be symmetric positive definite matrix, right? Okay, well, positive definite, right? Because by definition, a matrix is positive definite. If it's positive definite, then it's going to be symmetric, right? Okay, so your inner products on R2, right? What I'm saying is that the inner products on R2 would basically always look like this over here, right? You can't really find anything else, right? But anyway, let me that's jumping ahead a little bit. Let me just show that this over here, right? This gives me an inner product, and what I mean by that is this is a function on pairs of vectors that satisfies these three conditions, right? So I need to show that this function over here satisfies my three conditions. Okay, so I want to show that inner product defined this way as U times diagonal matrix times V transpose, right? Where your diagonal entries are 2 and 1, right? Okay, this is going to be an inner product, right? Now, this will work for diagonal matrices, but the diagonal matrices, the entries over here need to be strictly positive, right? They can't be negative and they can't be 0, right? So really what this hinges on is that these diagonal entries are positive here, right? Okay, so let's show that this is an inner product, right? So remember, we need to show three things, right? We need to show that you have linearity in the first argument, you have symmetry, right? And then you have your positive definite property, right? Okay, so to get the linearity in the first argument, it's not really hard, right? You use your definition of what the inner product is, right? So you take your first vector, multiply it against your diagonal matrix, and then you multiply it against the transpose of your second vector, right? Now this over here, this is just matrix multiplication, right? So you could regard the D times the W transpose as just a single matrix, right? And that single matrix will distribute over the sum of these matrices over here, right? And I get this line, and you want to notice that this line over here, the U D times W transpose is by definition U, the inner product with U with W, right? And likewise here, the V D W transpose is the inner product with V with W, right? Okay, so that gives me the linearity in the first argument, right? Right, the symmetry that I need to show now, right? That it and the symmetry means that if I have U then V or V then U, I get the same answer, right? Okay, and to show the symmetry, I can also just use the matrices, right? Okay, so I'm considering the inner product with U and V. Use the definition of the inner product, which is U times diagonal matrix times V transpose, right? Now this here, this is just a scalar, right? Okay, so if this is a scalar, right, and you just regard this as a 1 by 1 matrix, when you take the transpose of a 1 by 1 matrix with itself, right, you're just going to get back the same 1 by 1 matrix. So that's what I'm doing over here, right? This here, I'm just taking the transpose of it, and I'm going to get back the same thing because it's just a scalar, right? Okay, so hence I have equality over here, right? And now I use properties of transpose, right? Okay, so I use properties of a transpose. In particular, what I'm doing this is using this one over here, that if I have a product and I take the transpose of it, it's going to be what you're going to do is you're going to reverse the order and take the product of the transposes, right? So that's what I'm going to use over here, right? If I'm taking the transpose of a product of these here, right? You're going to reverse the order, right? So notice I have the V transpose here first, then the D, and then the U, right? You take the transpose of each of those and multiply, right? So I'm using really this AB transpose is equal to B transpose A transpose. This holds for a product of 2 and it will hold for a product of 3 matrices uh, as well, right? So that's what I use over here. And what I next thing I use is I have V transpose transpose, right? And anything transpose transpose gives me back the original matrix. So what I have is V over here. Now here I have D transpose, but you remember that this matrix D here, right? This is a symmetric matrix, right? Because if I take the transpose of D, right, the main diagonal remains the same. And when I reflect in the main diagonal, nothing changes, right? So in this case, D is a symmetric matrix. So any diagonal matrix is symmetric, right? So D transpose is just equal to D, right? And what I get is that when I work this out, I have UV, which is U times D times V transpose, is actually equal to V times D times U transpose, which is the inner product of V with U by definition, right? So what I did is I reversed the order in the inner product, right? And I have equality there, right? Okay, so that gives me the symmetry, right? And show the positive definite property, which is that first of all, the inner product of a vector with itself is going to be bigger than or equal to 0, right? What I do is I just expand, I put in components for the U and the U transpose, right? And I work it out in terms of the components, right? Okay, so the vector U is a row vector, U1, U2, right? And likewise, this vector U is a row vector. When I take the transpose of it, I get a column vector, U1, U2. And when I multiply this out, I'm going to get 2U1 squared plus U2 squared, right? And this over here, because the components U1 and U2 are real numbers, right? That means that this over here is non-negative, right? So that gives me the first part of the positive definite property, right? Okay, and the next thing I would need is I need to show this part over here that if the inner product of the vector with itself is equal to 0, then the vector must be 0, right? Okay, and well, I just showed that the inner product of the vector with itself I can write in this form using the components, right? Okay, so alright, so I just didn't really put much work in over here, right? So this is the inner product of the vector u with itself, and this is when you write it out in components, right? Okay, so what this is saying is that if this is equal to 0, right, then the u1 must be 0 and the u2 must be 0 because u1 and u2 are real, right? So that if I have that this side holds, then the u1 must be 0 and the u2 must be 0, right? Okay, and then conversely, if the u1 is 0 and the u2 is equal to 0, right? In other words, if I have the 0 vector, then put in 0 here and 0, put in the 0 vector in here and 0 vector in over here means that I'm going to have u1 is equal to 0 and u2 is equal to 0. And when I work this out, I'm just going to get 0, right? Okay, so one more time, if I start on this side over here, I will be able to show that the vector must be 0, right? And if I start on this side over here that the vector is 0, then I'll be able to show that the inner product of the 0 vector with itself is equal to 0, right? So that shows this, if you want, second part of the positive definite property, right? Okay, so this inner product over here defined this way, this function over here defined this way is in fact an inner product because it satisfies these three conditions, right? Okay, and I guess as I mentioned already, this here is not dot product, right? Why it's not the dot product is because this function here is not the same as this function here. Alright, so we just saw that if I have if I have a function on pairs of vectors, right, defined as U times a matrix times V transpose, right? In the case of when the matrix inside there was a diagonal matrix with positive entries on the diagonal, right? Then this turned out to be an inner product, right? Okay, so what we want to see is we want to see that actually more generally this is true, right? So instead of just having a diagonal matrix over here, I can have other matrices inside here, right? But they notice over here with this diagonal matrix is I really need that these entries over here to be positive, right? So not just non-negative, but also not equal to zero, right? Okay, so I need some sort of positive aspect to this matrix on the inside over here, right? But this matrix here, it doesn't always need to be a diagonal matrix, but it has to be positive in some sense, right? Okay, so I can have inner products defined as U times A times V transpose. And notice the structure over here is similar to the structure U times D times V transpose. But this A over here doesn't need to be a diagonal matrix. But it needs to have a certain positive property. And the positive property that it needs to have is that it needs to be positive definite, right? And your definition of positive definite is that matrix a symmetric matrix, is said to be positive definite if when you consider V times A times V transpose, right? And notice that's a sort of similar structure to what I have over here, right? Here I have vector times matrix times a vector transpose, right? So what you're going to get out of this sort of thing over here is just a scalar, right? Okay, this is slightly different because what I have is two different vectors here, U and V, right? What this is saying is you're going to use the same vector on both sides, right? Okay, so a symmetric matrix is positive definite if V times A times V transpose is going to be bigger than 0 for all non-zero vectors V, right? Okay, and it's said to be positive semi-definite if the same expression V times A times V transpose is bigger than equal to 0, right? So now positive definite allows the possibility of being equal to 0, right? For non-zero vectors V, right? Okay, notice this over here, this definition of positive definite must break down if the vector is 0, right? If the vector is 0, you're just going to get 0 times whatever the matrix is, will give you a 0 vector here. And 0 row vector times a 0 column vector would give you just a 0 scalar, right? Okay, so for this definition to make sense, you need to be looking at non-zero vectors V, right? Alright, so let's see an example of a positive definite matrix. Alright, so I want to show that this 2 by 2 matrix here, this is an example of a positive definite matrix, right? Okay, and to show that it's a positive definite matrix, I need to show that it satisfies this condition here, right? So that if I have a vector, multiply it against the matrix, and then multiply it against the vector itself, transpose, right? Then that is always going to be bigger than equal to 0. Bigger. The V times A times V transpose has to be bigger than 0 for all non-zero vectors in R2, right? Okay, so let's show that, right? Okay, so here I'm using instead of using V, I'm just calling it X, right? It's the same working, right? It's just a different name, right? Okay, so I have X times A times X transpose, and I can write the vector X in terms of the components X1 and X2, right? Alright, so I'm considering so my vector is 1, my matrix is 1 1 1 2, so that's the matrix A 1 1 1 2. And I'm considering your product X times A times X transpose, right? Because that's your definition that you use, right? You use this in your definition to show that your matrix is positive definite. Okay, so we work this out, right? And you just multiply out over here, right? When you multiply out, what you're going to get is when you multiply this row vector against your 2 by 2 matrix, you're going to get a next row vector, and then you have a row vector against your column vector. And then you just multiply out everything over here, right? Now, once you multiply out everything over here, you're going to get terms that involve product of the x's, right? And one thing you can notice over here is that what these terms are, they really just come in, the coefficients here are coming from your matrix, right? So for example, I have x1 squared, that's corresponding to this one over here, right? I have x2 times x1, that's corresponding to this one. I have x1 times x2, that's corresponding to this one. And then I have x squared times 2, that's corresponding to this 2 over here, right? So that would be a fast way to get it. Or you could just multiply it out, right? Okay, so once I have this expression over here, right, what you want to do is you want to complete the square on this expression, right? Okay, so here what I have is 2 x1 x2, right? I have x1 squared, right? And in order to write this as a square, I need x1 squared plus 2 x1 x2 plus x2 squared, right? And then, so the 2x2 squared I split into x2 squared plus an x2 squared, right? And I took one of the x2 squareds and I put it into this expression here, right? And you want to notice that this is just x1 plus x2 all to be squared, right? So I complete the square, well, didn't complete the square, I just wrote this as a square over here. Okay, so this expression here, right, I can write as x1 plus x2 squared. And then I have an x2 squared over here, right? Okay, so my x times a times x transpose I wrote as a sum of squares like this, right? And you want to notice that this here is always bigger than or equal to 0, right? Okay, because I'm looking at real numbers over here, and this is a real number squared, and this inside here is also a real number squared, right? So it's bigger than or equal to 0, right? What I need to justify is that once any of these components are not equal to 0, right, then I'm going to get strictly bigger than 0, right? Or in other words, what I need to show is that the only way that I'm going to get a 0 over here is if both the x1 and the x2 are equal to 0, right? And really, you could just... Okay, so what you're doing now is you're looking at this and you want to see when it's equal to 0, right? Okay, so the xa x transpose is equal to 0, and this is the xa x transpose. That's equal to 0 only if the x1 plus x2 is equal to 0, right? And the x2 is equal to 0, right? The only way that this expression is going to be equal to 0 is if the x2 is equal to 0, and if what's inside here is equal to 0, right? Okay, and from that, what you're going to get is you're just going to get two equations here, right? That x1 plus x2 is equal to 0 and x2 is equal to 0, right? And if the x2 is 0 and you put the x2 is equal to 0 inside there, you're going to get that the x1 is equal to 0, right? So this over here implies that the x1 and x2 must be 0, right? So one more time, right? In order for this to be equal to 0, it means that this expression over here would need to be 0. And in order for this expression here to be equal to 0, the x1 plus x2 has to be 0 and the x2 has to be 0, right? Which means that the x1 must be 0 and the x2 must be 0, right? So the only way that this is going to be, this xa x transpose is going to be equal to 0 is if x1 is equal to 0 and x2 is equal to 0. In other words, this is 0 only if I have a 0 vector, right? Okay, so it's only, this is 0 only if I have a 0 vector, which means that in all the other cases for any non-zero vector, right, and any non-zero vector means that one of the x1s or the x2 has to be non-zero. It could be negative, that's fine. The main thing is that one of the x1 or the x2 has to be non-zero, right? And if one of the x1 or the x2 is non-zero, then this entire thing over here is going to be bigger than 0, right? Okay, so that shows that xa x transpose, right, when you work it out, has to be bigger than 0, right, for all vectors that are not equal to the 0 vector, okay? And therefore, the matrix A is positive definite. Right, and this here is an example of a positive definite 3 by 3 matrix, right? Okay, and how they show that it's positive definite is the same sort of working in a 2 by 2 case. You consider in the expression z. Okay, it's slightly different over here. What the z here is in fact a column vector, right? So in order to get a row vector on this side, you take the transpose, right? So the notation is a little different, but the method is the same, right? What you do is you put in your components, you expand it out, and then you really just express everything as a sum of squares, right? Okay, so for this class, to show something as positive definite, we'll restrict to 2 by 2 examples, right? But this would be how you do it for 3 by 3. It's a similar method, right? But in general, if you're going to show that a matrix is symmetric, a next way to do it is, and this is something that we will get to eventually, is that a real symmetric matrix is going to be positive definite if and only if its eigenvalues are positive, right? Okay, and we would need to know what an eigenvalue is to understand this, right? But if you want to check for positive definite, you have other ways to check aside from the definition that I gave you, right? And one way is to look for the eigenvalues, right? And looking for the eigenvalues really means that you're really going to transform you diagonalize your matrix so that you're going to get you diagonalize your matrix and the resulting diagonal matrix out of that diagonalization process. You want to check on the diagonal here that all your entries on the diagonal are positive, right? Okay, so right, but for purposes of this class, the positive definite to check, right? The method that we're gonna to check if a matrix is positive definite, we're gonna restrict the 2 by 2 cases, and this is the method that we would use here, right? Okay, so now that we know what a positive definite matrix is, right, we can use it to determine the type of inner products that we have on Rn, right? The proof of the linearity in the first argument and the proof of the symmetry is the same as what I did across here, right? Because what I did across here, I didn't use any real property of the matrix D, right? I just used the fact that it was a matrix, right? A square matrix, right? Okay, so you could take a look at what I did for this case over here to show that this function here is an inner product. That those arguments for the first two cases would work for these two cases as well, right? Okay, what's different is the positive definite condition, right? Okay, so well, remember what the condition is, right? So what I want to show is I want to show that the inner product of the vector, the function, right? When I take I consider the function the inner product of the vector with itself, right? This is going to be bigger than or equal to 0, right? For all vectors, and the only way that I'm going to get 0 here from this inner product is if the vector is actually equal to 0, right? Okay, and this is an only if and only if statement, right? So inner product is equal to 0 implies that the vector is equal to 0, and if the vector is equal to 0, then the inner product is equal to 0, right? This direction going from the 0 vector to show that the inner product is 0 is the easy part. The harder part is, given that the inner product is equal to 0, the inner product of the vector itself is equal to 0, implies that the vector is equal to 0. Well, that's slightly harder, right? Okay, so that's what we want to show, right? So, well, how do we do that in this case here, right? So really, it's just going to come from the definition of what a positive definite matrix is, right? Okay, so what is a positive definite matrix? A positive definite matrix is if you have a vector and you consider vector times A times same vector transpose, right? That is always going to be bigger than 0 for all non-zero vectors, right? Okay, so let's see how that relates to our positive definite property that we need to show for the inner products, right? Okay, so this is the definition of a positive, using the definition of a positive definite matrix, right? If I consider inner product of U with itself, right, that's equal to U times A times U transpose, right? So that's just a definition of this function here that I'm using, right? And that is in fact bigger than 0 if the vector is not equal to 0. So this part over here is coming from the definition of the positive definite matrix, right? Okay, so inner product of U with itself, which is U A U transpose, right? That's going to be bigger than 0, right? Because matrix A over here is a positive definite matrix. This is going to be bigger than 0 once your vectors are non-zero, right? And if your vector is actually equal to 0, right, well then what you're doing is you're multiplying by a 0 vector here and a 0 vector here, right? Okay, so multiplying by a 0 vector will just give me a 0 scalar over here, right? So that's when the vector is equal to 0, right? Okay, so let's just summarize what we have over here, right? This inner product over here is going to be bigger than equal to 0, right? So it's bigger than 0 with the possibility of it being equal to 0, right? So combining this, the fact that it's bigger than 0, right, and the possibility that it could be equal to 0 gives me the fact that this inner product over here is bigger than equal to 0, right? Okay, so that's your first condition for a positive definite, right? And then the next condition is you want to look at if you have inner product of U with itself being equal to 0, right? If you have inner product of U with itself being equal to 0, right? The only way in this situation when the inner product is defined as U A U transpose, right? And where A is positive definite. The only way that this is going to be equal to 0 is if the vector is equal to 0, right? Because if the vector is not equal to 0, then it's going to be bigger than 0 by definition of positive definite matrix, right? Okay, so this statement over here being equal to 0 means that UA transpose is equal to 0. And that is only true only if U is equal to 0. So that gives me going from inner product of U with itself being equal to 0 to U is equal to 0. And for the reverse, it's easy, right? What you're doing is you're just saying if your vector is 0 over here, then once you feed 0 into this expression for the U, right, you're just going to get scalar 0, right, which is this here, right? Okay, so really this condition here, all you're doing is you're just using your definition of a positive definite matrix, but you just need to rearrange it slightly, right, to match your definition for positive definite in the case of an inner product. So far what we considered were inner products on Rn, right? And first one that we looked at was dot product, right? Dot product would be an inner product on Rn, and the other inner products on Rn that are not probably necessarily dot products you can get by using, well, you can use diagonal matrices where all the entries in a diagonal are positive, or you could use positive definite matrices, right? And this would be the form of your inner product, right, in both cases, right? U times square matrix times V transpose, right? Okay, so this is for inner products on Rn, right? Now let's consider a vector space that is not Rn, right, which is this vector space of polynomials, right? Okay, so for your vector space of polynomials, right, and this is polynomials of degree at most n, right? What we want to do is we want to define an inner product, right? And this inner product that we're going to define on polynomials of degree at most n, right? We're going to do it via integration, right? And we integrate in from 1 to minus 1, right? Why are you going to use 1 to minus 1? Well, that's just sort of standard theory, right? It leads to some standard definitions. Okay, so I have for polynomials of degree at most n, I define an inner product, right? And remember what you're doing is it's a function on pairs, right? And it's pairs of vectors, but in this case the vectors are polynomials, right? So you have pairs of polynomials denoted by p of x and q of x, right? And what you want to do is you want from this p of x and q of x, you want to combine them to get a scalar, right? And how you combine them to get a scalar is you multiply them, right? Just multiply the polynomial. So normal polynomial multiplication, which would give you a function of x, and you integrate that function of x between 1 and -1 to give you a scalar, right? Okay, so this here, you can show that, and we will show that this in fact is an inner product, right? Okay, so to show that this function over here is an inner product, you need to show, well, the three things: linearity in the first argument, symmetry, and positive definite, right? Okay, so to show linearity in the first argument, really, well, this first vector over here, you write it as this linear combination. You just use your definition of what your function is in this case, right? Which is you multiply first argument by second argument and you integrate from 1 to -1, right? But notice inside here what you have is you have a linear combination of two functions of x, two polynomials with times this polynomial over here, right? And you could always just multiply this out, right? Now when you multiply this out, you're going to get px times r of x with the scalar a, right? And you can pull the scalar a out of the integration. And then you're going to have qx times rx, and you can pull the scalar b out of the integration, right? So this is just using linearity property of your integrals, right? And once you have this over here, right, you would just want to notice that this here is the inner product of p of x with r of x, and this here is the inner product of q of x with r of x, right? And you pull your scalars a and b outside, right? So that in fact gives you your linearity in first argument condition, right? That it holds. To see the symmetry, right? Again, you're just using the definition of the function, right? So if you have the p of x and q of x, how you combining them is you multiply both of them and you integrate, right? But then inside this integral, it doesn't make a difference if you switch the order, the polynomials, right? When you integrate it, you're going to get the same thing, right? Because it's just the same function, right? And this over here is just inner product of q of x with p of x, right? All right. The third one, the positive definite, I will just talk about this part of it, right? That the fact that it's bigger than or equal to 0. Okay, this part over here to show that if your inner product of a polynomial with itself is equal to 0 implies that the polynomial is equal to 0. The proof is in the notes, you could take a look at it, but this just involves a little bit of analysis and so, right, which is probably not within the scope of engineering maths, right? But you can read it if you understand, if you know what continuity means for a function, right? Okay, so I'm just going to show this first part over here, right? So if I have a polynomial and taking the function of the polynomial with itself, right? That just means I'm going to integrate the product of p of x with itself. So this is the polynomial squared, right? But this is just some function squared, right? And the function squared is always just going to be bigger than or equal to 0, right? Anything, remember, this function is giving you real values and you're squaring those real values. So whatever you have over here is always going to be bigger than or equal to 0, right? So this function is a non-negative function. In other words, it's always above your x-axis, right? And if you integrate it, right, you're always just going to get an answer that's bigger than or equal to 0, right? So that's showing this part over here, right? And as I said, you can similarly show this part. And that will justify that if I have a vector space of polynomials, I can define an inner product this way by taking your two polynomials over here, right, and multiplying them and then integrating between 1 and -1, right? Okay, so why you'd care about an inner product of this sort of form here, right, is that this sort of inner product is used in Fourier series, right? Okay, so let's recall that if I have a function, right, you can find its Fourier series, right? And how you find its Fourier series is the Fourier series would be a constant term, right, with a series involving cosines and sines, right, with coefficients here. The a is over here and the b is over here, right? And you have formula for those coefficients. Right, and the formula for those coefficients actually involve integrating your function, right, against a cosine, right, between values pi and minus pi, right? and you want to compare it to what you have over here, right? It's very similar to what I have over here, right? You have a function and you integrate it against a cosine. Over here, you're integrating against a cosine. Here, this is function integrated against an x function, right? Okay, so your coefficients for your Fourier series, right, you actually get by using inner product that is defined in this sort of way, right? You may need to adjust by a constant over here, 1 on pi, right? Anyway, so this sort of inner product over here is used in your Fourier series theory, right? And if you see how this is stated that if you have a function, right, and you have the expression for the Fourier series, the coefficients you actually obtain in by taking inner products, right? Inner product of the function with cosine, right? And this inner product is defined in this way, right? Okay, and how these formula are actually derived, right? What you do is you use the fact that the sines and the cosines and the constant term would in fact be orthogonal, right? And you use the orthogonality to in fact obtain these types of formula, right? Okay, now that's beyond the scope of this course, right? But the point is this sort of inner product is useful when you're working with Fourier series.